Okay, hello everyone. Let's get started with our next lecture. Hopefully this format is at least acceptable for now. Like I said, hopefully soon it gets a little better, but for now let's just stick with this and get started. Okay, so today is lecture number 21. Still we are on chapter 12. We're going to go over stuff today that's on pages 314 to 328 in the text. For next class, there's no reading because the stuff I'm going to talk about next class is not in the book, so it'll be really important to pay attention to that lecture and get all the information from it. Homework, still trying to figure out how that'll work. Me and Ben are talking about how we'll get that done right now, so sorry for that little gap in, you're practicing. If you feel like you need to practice and get a better handle on these ideas, just go into the book for this chapter and look for some problems that look like the stuff we're doing, and just go through them. Likely some of those problems will later be homework problems when we figure out how to get that organized. Okay, so today we're going to go over the vector or cross product, right? It's a new type of algebraic operation between two vectors, right? Before we saw what was called either the scalar product or the dot product. This is a different type of vector multiplication, so we're going to learn about that today. And of course it has application to torque, which we will also talk about today again, right? So vector products and cross products have application to torque and rotational motion, which is why we're going to be going over it today. And lastly, we're going to define the concept of angular momentum. Okay. So, you know what? This is going to be really difficult to do in this format. So, the next little bit, I'm going to move my camera. So, pause. Okay. So, here I am again. I can't quite see myself because the camera's not pointed at me in a really good way. So, let me move this. Okay, hopefully you can see me. I can kind of see myself a little bit because I have a mirror back there. Okay, so we've been talking about rotations just in the sense that we're looking at some object and this object's rotating around, right? We might say that the object's rotating clockwise or counterclockwise, right? But what if the object is rotating in some more complicated way? Right, how do we describe this rotation? Right, this would be really difficult to try and describe, what's happening in this book. So we describe a rotation by assigning a vector to it in the same way we would assign a vector to a linear translation or a velocity or something like that. Okay, so the way we do this is with what's called the right-hand rule. The right-hand rule means I take my right hand, I curl my fingers around in the direction of the rotation, and then whatever direction my thumb points in, that's the direction I assign to that rotation. So if my book was rotating like this, right, I would curl my fingers around in the direction of rotation, and I would say that book is rotating up, right? It's spinning up, right? Because that's the direction my thumb points in. Likewise, if the book is going around like this, right, I curl my thumbs around the direction of rotation. My thumb's pointing towards me, so I would say this is spinning towards me or to the positive z direction or whichever direction this is defined to be, right? So I can, any kind of weird rotation, I can just assign to a vector, right? And then I know how that object is rotating and I can describe that mathematically. Okay, so hopefully that was clear. It's a bit more clear, obviously, if we're in person and I'm explaining it. So back to the math now. All right. So, this can also be used to assign a direction to a torque, right? In the same way that we could say an object is rotating in some particular direction, we can also say we're applying a torque to it in some particular direction, and that is just the torque that would cause the object to rotate in the same direction as is defined by the right-hand rule. Okay, so if we took some object, some circular object like this, say it's spinning, right, along this axis of rotation, right, we call this spin up, it's spinning this way, right? If we apply now tangentially some force, right, where it's all along the tangential direction, you have the torque equals RF, right, where this is some tangential force. And now we can assign vectors to both of those things, both to the force, which is some linear direction here, and the torque it causes, right? So actually, to write this more properly, this would just be the tangential component, and then I'd have some unit vector, right, which I'll just call t for lowercase t for torque, and that would be this unit vector there. Okay. So if I'm applying this, so now the question is, how do I get to some form, right, where I have these guys in here without having to define this unit vector in some awkward way, right? How do I get to that naturally? Well, we know that only tangential components give rise to torque. And if I have some general vector, which now I'll also write with an F, right, just to be a little confusing, but so now this is some other more general vector for force, right? Now I get some should be absolute value. Now I get some torque out of that according to what angle it's applied at, right? So that sine theta gives me what component I have along the tangential direction, which is how much torque I'm applying, or how much of that force goes into torque. So this is sort of the opposite case of what we had when we were investigating work, right? If you recall, when we were talking about work, we had work as defined distance times the force along that distance, right, which ended up being dF cosine theta, right? So for work, we want to be applying that force along the path the object takes to get the maximum amount of energy transfer. But for torque, we want them to be perpendicular, right? Which is why we have a sine here and a cosine here. So when we were studying work, that's when we defined the scalar product, which allowed us to take two vectors, excuse me, and take two vectors and intuitively get a way to say how much they are aligned with each other, right? How parallel they were, and then multiply that by their magnitudes. All right, so if we had some general displacement vector d, which had some, x component and some y component, right? We took some other force vector that perhaps has some x component like this and some y component like that, right? And then we took d, or could take d dot f, and then we would just multiply ax bx plus ay by, and then again if there had been a z component, right? So now we're going to define a new type of vector product to define situations where we have some torque or some rotation that's being applied to an object. And now, so we're going to define this new product for vectors as the vector product or cross product. Right? It's called the vector product because the thing we get out of it is going to be a vector, right? That's going to be different from when we were taking dot products. So when the thing we got out of dot products was a scalar, right? These are all scalar numbers multiplied and added. We don't have any of these unit vectors in there. So the thing we got out of that was a scalar, so we call this the scalar product. Likewise, when we have a vector product, the thing that comes out of it is going to be a vector. It's also called the cross product for the same reason the dot product is called the dot product. When we write a cross product, we do it with a cross multiplication symbol, right? Dot product we write with a dot, of course. All right, so what is the cross product? So the easiest sort of geometrical definition is if we have two vectors out in space, say A and B, again some angle between them. The result of that cross product is going to be the magnitude of A times the magnitude of B, much like the dot product, but now times the sine of the angle between them, and some new vector, right? Some new unit vector. And this unit vector has a property that it's perpendicular to the other two vectors, right? So if I have two vectors, I can, if I can put those two vectors in the same plane, right? If they're not like crosswise like that, if they're in the same plane like this. Excuse me, I had to clear my throat a little bit. These two vectors, if they're in the same plane like this, that new vector that's the result of the cross product is going to be pointing perpendicular, right? So let me get a couple more pens and maybe I can demonstrate. Right? Suppose I have two vectors sitting out in space, right? I move them around so that they're together, right? Now I have two perpendicular vectors. Now if I take the cross product between these two vectors, the result's going to be a new vector that's going to point perpendicular to both of them. Okay. So that's how we write down the mathematics of the cross product. Right? And if you're confused about, well, does it point this way or does it point this way? Does it point up or down? That's defined by, again, the right-hand rule, right? So this is just a convention that as long as we're always consistent with it, it always comes out the right way. So as long as we're doing everything with our right hand, right, not our left hand. If we do things with our left hand, we get the opposite result. So we take our right hand, and actually, I've drawn this wrong. This is incorrect. Because the way the cross product works is I take A, the first one, I cross it into B, and that's the direction it points in. So actually, this guy should be pointing down this way, all right? Because we have A cross B. So why did I make that mistake? I made that mistake because the order of this matters for that exact reason, right? If I had written this B cross A, that would have been the other vector I had drawn earlier because I would be going B cross A. So this is something, this is something that's a little different from what you're used to because you're used to multiplication, it not mattering which order the things are multiplied in, but for the cross product, it does, right? If I reverse an order of a cross product without thinking about it, all my answers are going to be off by a minus sign, which maybe I subtract or add that to other things and get, something that's very different than what it should be. So you have to be careful about getting this stuff in the right order, and always be careful because I've been doing this for years and I just made mistakes. So it's important to be cautious and careful. Okay. So, one thing to mention just about the cross product is that it only makes sense in 3 or more dimensions, right? If I have a 2-dimensional plane and I say I take the cross product between 2 vectors in that plane, well, it's not defined, right? Because that new vector would have to point out of the plane. So only in 3 or more dimensions is the cross product defined. Okay, so the easiest example of a cross product is between the unit vectors that define our 3-dimensional rectilinear space that we think we live in. Okay, so we've got the x unit vector, which we could also call the I unit vector. We've got the y unit vector, which we could also call the j unit vector. And we've got the z unit vector, which we could also call the k unit vector. Okay, so let's look at the cross products between each of these unit vectors. So I have x cross y, let's say. So if I were in class, I would have you guys try and guess, but since you can't guess, I'll just tell you, right? I take x, I cross it with y, and of course I get something that points in this z direction. So x cross y is z. Excuse me. Sorry. So the order is important, right? If I had gone y cross x, I would have gotten negative z, but here we have z, so x cross y equals z. Likewise, if we have y cross z, so going around cyclically in this space, we get x, right? Y cross z equals x. And then we have z cross x equals y, right? And this completes sort of what we call a cyclic permutation, right? This goes around and around and around, and if we took x cross y, we get back to z, et cetera, et cetera. So the main thing to remember with the cross product that'll help you actually do them is remembering these relations, right? Because almost always we're going to be writing vectors in terms of the unit vectors, and then the cross product distributes out in the same way that the dot product does or a regular multiplication product does. So knowing these relations is what's going to let us, quickly solve for the answers to cross products, right? And we'll do some examples of that in just a second. But one more thing I want to mention about this is that this cross product actually defines our three-dimensional coordinate system, right? You may have at some point drawn a coordinate system like this and been told that's wrong, and then maybe you said, well, why is this wrong? And maybe the person who was talking about you didn't really know. Why is it that we put the y over here and the z over here? Well, the answer is because that we want our three-dimensional coordinate systems to follow this same sort of logic that the cross products do, right? We want x cross y to equal z, we want y cross z to equals x, we want z cross x to equal y in every coordinate system that we draw, right? And we want it to be consistent or else we're going to make mistakes. So we always have the coordinates in this order, right? I could have a coordinate system that looked like this, but this still follows that same rule, right? Because x cross y is still z, z cross x is still y, etc., etc. Well, one more, etc. So that's how these coordinate systems are defined. Sometimes you will see a coordinate system where they're reversed, like I had them written originally, and this is called a left-hand coordinate system because it would be the right coordinate system if I was using my left hand, which no one does. It's just what it would be called if you use this, but there's no reason to. Okay. So before we do a couple examples, I want to go through the rules for a cross product. So the rules for a cross product are just the laws, right, that tell you how they work. So the first one is sort of the most important because it's the one that's different from the algebra that you're used to, and that's that A cross B is equal to negative B cross A. Right? So that we have this identity for the cross product. The cross product distributes in the same way that you're used to. Right? We take derivatives in the normal way with a little proviso. Sorry, that's my computer making that noise in the background. It does that when it can't make up its mind whether it's connected or not. I figured out how to turn it off once, but that was like hours of work, and since that computer crashed and was repaired, it's making it again. Anyway, so I take the derivative of a cross product and I get my product rule going out, and now it's the same as what you're used to, except I have to be really careful to keep them in the correct order, right? In this order, in the same A then B order that it was in this original expression, right? This bit and this bit obviously can be interchanged, but this bit and this bit can't, and this bit and this bit can't. One more thing that's really important to realize about the cross product is that if I have a triple cross product, which is something you run into occasionally, so something like this is not equal to A cross B cross C. Those are different things, right? It's not associative. It matters what order you do the cross product operations in, right? If I had three vectors, in principle, these don't give me the same things if I had done them out in a different order, right? So this is another way that's different from what you're used to from regular multiplication. Because of course if I have scalars, right, AB times C is the same thing as AB times C. But for cross products, this is no longer true. Okay, so that distributive rule for cross products combined with our knowledge of how the cross products work for the unit vectors gives us a good way to calculate the cross product more general vectors without trying to figure out the angle and then taking the sign and then trying to figure out how to define that third direction that resultant vector is supposed to point in. So let's take an example by way of explanation and assume we have these two vectors. A is going to be equal to 2z hat plus 1x hat, and B is going to be equal to 1y hat plus 3x hat. So I'm going to draw our three-dimensional coordinate system here, right? X, Y, Z. And now I'm going to draw these two vectors on here. So let's draw this B first. That's 3 clicks over this way and 1 click up. So right there. So I'll draw a vector that points to that. That'll be my B vector. And to be clear, that's right there. So that's just in the YX plane, right? It has no Z component. Okay, likewise, the A vector has no Y component, so that's going to be in the XZ plane, so down here. And that is 2 clicks along the Z axis and then 1 click over on the X axis, so right about there. Okay, and then we'll draw in that. Okay, so this is A vector. And now we want to find the cross product, right? Let's calculate A cross B. So we just write in those vectors. It's not necessary to write the ones, but I'm just doing it to be clear. Okay. Now we just distribute this out. Okay, so we know from our little table earlier, right? X cross Y equals Z, Y cross Z equals X, Z cross X equals Y. We could also get that again by doing that right-hand rule on all those little bits. So we know that Z cross Y is the opposite of Y cross Z. So we have to flip the order, which means we get a negative X. Right? So a 2 times a negative X hat. Right? The next one, Z cross X, we know that that's just Y hat. And then the third term, all right, no, there's more than 3 terms. The third term is just Z hat. Right? X cross Y equals Z. And then now the fourth term has 2 of the same unit vectors in it. So when we have 2 of the same unit vectors, that's always 0, right? Calculating the cross product is asking how perpendicular are 2 things. And if 2 things are parallel, they are not at all perpendicular, so we get 0, right? The angle between them is 0, sine 0 is 0. So now we've got that A, so we start off with the A vector, A cross